Thank you. So, good morning, everybody. This is our second last week of classes, and today we're going to be covering our last lecture on Unix type topics. Wednesday we're going to be covering some absolutely crucial C material, and then next week we're going to finish off with some C material, and then on Wednesday we'll have a review session. Please bring your questions. So, it is good and proper to be, yes?
Is there any lab on the last Wednesday?
No.
Okay.
There are 10 labs. You'll be doing labs 9 and 10 this week. There are no labs next week. Try not to be too enthusiastic. Lab 9, by the way, I would consider pretty easy, and lab 10 is, you've seen it? You've taken a look?
No, I'm just guessing what you're like.
It's going to be on pipes, filters, and regular expressions.
It's going to be lab 3, part 2, isn't it?
No, not quite so severe, but.
Sorry for bringing up everyone's
yeah. Anxiety level in the room just rises. No, basically what lab 10 is it's a set of, I think, 30 odd problems where you have to take a big directory and perform correct search operations to perform, extract out this correct, this set of files from all of these, extract, perform find and replace operations, that sort of thing, which is all very useful, and it's all stuff that requires practice to really sort of hammer home. So that's what lab 10 is. Lab 9 is on documentation. Yes?
For the Unix part of the exam, what I've noticed when we got doing the labs, they're mostly just tools. How are we actually graded after the exam? Because I never really do questions.
This is an excellent question. I'm happy that you brought it up. For the people listening at home, the question is, what do we do about the Unix part of the exam? Because basically all of the Unix tools have been, pieces of software that we've been learning how to use rather than, they haven't been programming tasks, right? Well, if you want a very good example of the way in which I intend to test you on the Unix stuff, I have actually posted last year's exam. Now, last year's exam was based on a 24-hour sort of format in the same way that I was doing the 1MD3 exams and tests up to that point. I have since departed from this model of testing, owing to the fact that we are now in person fully, and the fact that apparently a large number of people were simply paying other people to write their exams for them. Looking at you, business faculty. Actually though. So basically it's not really feasible anymore to not have exams occur in person. So you can expect this year's exam to be quite a bit shorter in terms of the amount of material you'll be asked to produce. The questions will be shorter versus what's currently posted online. However, I really like last year's exam. I'm a little bit smitten with it even still. A year later, and I still kind of love that exam. So I think that grade A #1 preparation for this year's exam would be to perform last year's exam. Essentially, the form of the exam was this. I wrote a program. I poked a few holes in it where basically I punched some of the functions out and said, okay, you do each of the functions I've punched out of this program as a C programming question, right? And there was some linked list stuff in there. And then, for the Unix side of things, I expected you to make a make file or pieces of a make file that, would compile the program. I wanted you to set it up for documentation generation, as we're going to talk about today. And I wanted you to do some profiling, basically questions like how many times is line X in, file Y run, actually, so like you'd have to perform coverage testing. Given that it's an in-person exam, I'm going to permit you to have a double-sided crib sheet, single-page double-sided crib sheet. I highly recommend putting all of the commands and all of the Unix commands, make it a Unix command reference sheet for your exam, because I'm not going to be testing you outside of the programs and commands that we've actually covered, obviously. I hope you don't have to put anything really basic on it, like ls or cd. That would just be a waste of space. Unless it's not a waste of space, in which case it really, really should be there. Yeah, so that's the essential character of the exam, or it was last year, it's a big program with a few pieces pulled out of it that you're asked to perform some of the tasks you've been performing in lab so far on that program. Including piping in test cases and doing like a diff test. That was another one on there. So it was fairly comprehensive because it was a bit of a longer exam. This time the exam is shorter, so it will not be able to be as comprehensive. But the specific topics that are going to be on the exam are of course going to be a secret, so that you have to study everything. Ha! Because that's how it works. Is that a sufficient explanation? Are there any other questions about the exam? The exam will be held at 9 o'clock in the morning on Friday, August 5th, I believe. Let's see here. Yes, August 5th. The exam will be held in LRW B1007, which is the very large lecture theater that's often used for testing in that new building that is where the Phoenix used to be. Yeah. That room has electrical outlets at each desk, so you're expected to bring your own computing equipment for the exam. Please ensure that your laptop is set up and prepared for the exam prior to the exam. So make sure that you are well capable. If you're using Pascal, make sure you know how to get a zip file and all of those files onto the Pascal server so that you can actually do stuff on it. If you're using, Windows subsystem for Linux, then you should know how to use that. My advice to you, have two ways of doing it, so that if one of those goes down, for example, the Pascal server ceases to function mysteriously for some reason, I hope it doesn't, but when you're connecting to remote servers, there's always the possibility it goes down even for 10 minutes. 10 minutes is a long time on an exam. Try to make sure that there is a secondary way that you can access a bash prompt and perform these tasks that I'm going to set for you. Okay? That's my advice. Question?
Is it open book?
No, it's not open book. You have as aids your two-sided cheat sheet. You have the man pages, and that's it. So no Googling, no internet access, because aside from that internet access which is required to log into the Pascal server. Make sense? Question?
What about previous assignments that are already on Pascal?
That's a good question. I'll get back to you on that one. I'm thinking that we might have to, yeah, that might be a vulnerability. I'll think about it. You're late! Quickly, quickly, quickly! Fortunately, we've just been talking about the exam, so, you might want to check the recording. So, I think that's everything. I've been not mic'd this whole time. That's okay. All right, so, are there any other questions? Well, we might as well move on to our lecture for today. So, I almost want to start with the end because the documentation stuff is the stuff you're going to be doing in lab today, so to some degree it makes sense to start with it. You guys mind if we jump ahead to the documentation stuff? Yeah, okay. Cool. You guys are so cool. Right, so, documentation. The greatest obstacle to discovery is not ignorance, it is the illusion of knowledge. We're going to talk, those of you who came to this class or came to this stream from the engineering stream, to what degree do they emphasize comments to you? Yeah.
Pretty high.
Pretty high? Good.
They make us comment every function, and then anywhere where something happens.
Good. And they grade you on that?
Just like, is it there or not?
Mm-hmm. Okay,
I can
good.
second that.
Hmm?
I can second that.
Cool. Excellent. That's good. So, software engineering for a very long time has been software engineering. In comparison to other engineering disciplines, software is a much less repeatable type of project. There's this famous statistic that gets quoted, which is probably a bit old now, that half of all software projects fail, right? Whether that's fail to be completed on time, or fail to work at all, or have to be thrown out and restarted. Software projects are difficult to actually pull off in comparison to something with very known procedures and properties, like, for example, building a bridge or a building, or, building an engine or something of this nature, right? The sort of underlying problem that causes software to be this unreliable is, and this sounds a bit conceited, but it happens to be the case, software programs just happen to be the most complicated things that human beings have produced, aside possibly from the CPUs that they run on. So due to this sort of absolute deluge of complexity, it's very, very difficult to tell what software is actually doing. Like reading code, as I'm sure all of you found out in Lab 3, is a non-trivial task. It is one of the higher skills of software development is being able to understand someone else's code. So, in the face of this incredible complexity, the best weapon that we have is for people to be rigorous about telling other people what the heck it is that they're even doing. This is commenting your code. However, commenting your code is a skill in and of itself. It's not sufficient when writing a function to simply write, this is a function called this, right? There are specific things which are useful and interesting and pertinent, which must be communicated in the form of a comment. Many comments, and I know I'm like explaining a meme, which, you know, removes all the funny, but, you know, what do you expect at this point? It's me. You often get comments of this type, which are things that are explaining the complete bloody obvious, right? This is not good commenting. We sort of sometimes fall into this trap with comments, where you are expected to write X lines of comments, so you just fill it up with, you know, whatever, you know, pointless information you can, you know, deduce. But, you know, there are much better approaches, and we're going to talk about some of those approaches and some of the tools, well, one tool in particular, which can help you to generate useful documentation. So, documentation. Some languages, such as everybody's favorite Haskell, are somewhat self-documenting. In Haskell, as long as you're, you know, writing Haskell well, your function names are going to be reasonably cogent, and since it's the function name you're dealing with most of the time when you're programming in Haskell, they tend to be a bit more self-documenting than something like C. C is not a self-documenting language. You cannot rely on the structure of the code itself to be readable. Code can be documented either in the source code itself, which of course is useful primarily to programmers or people who are going to actually be looking at the source code, or in an external document, which is useful for the rest of humanity. So, external documentation. Sometimes you see, like for example, take a compiler. Let's say you're working with some obscure compiler. Very often that compiler will have a language reference manual and a usage reference manual. These are big, thick books that tell you how one considers a program to be properly constructed according to the compiler, how to use the compiler, what the options are, all of this kind of stuff. Some of it basically boils down to a more explained, more expanded version of the man pages, and some of it is, you know, tutorializing as well. Tutorials would fall in this category as well. So, a recent trend in programming is literate programming. Literate programming is when the source code is annotated in such a way that some or all of the documentation can be generated automatically using documentation tools. What we're going to be talking about a tool called Doxygen, and Doxygen falls into this category of literate programming because how it works, broad strokes, you provide special types of comments inside of your source code with special symbols. The special comments are then extracted and parsed and turned into documentation by the Doxygen program, which is highly configurable. So, documentation do's and don'ts. So, this is what you should do. Write your program, or write your documentation for your audience. If it's inside of the programming file, you can assume whoever is reading your code is a programmer. and you can assume some degree of familiarity with the language that this code has been written in. It kind of silos people a bit, but if you're writing comments on a Java program, you can assume whoever's reading it knows at least enough Java to be able to, understand the structure of the program. Use clear variable and function names. This is self-documentation. So, although it is more characters to type, the only time that it is appropriate to use variable names like I and J, K, X, Y, Z is when you're sort of in the typical and accepted uses of indexing variables, right? So if you're going through a loop, it's fine to use I to go through all of the indexes in a list. Otherwise, your variable names should mean something. They should describe what they are. The same applies for function names. Function names in particular, because, while it is a terrible sin to write a variable name that has nothing to do with what the variable's actual function is, it is high treason to write a function that has a name that's nonsense. So, comments should go, A, at the top of the file. Each file should have a comment at the top indicating several different things. Good things to include are who wrote the file, when was it last modified, any copyright information that might be pertinent. Comment the tops of functions. Describe what is the function meant to do. What does it take as inputs? What does it produce as outputs? What are the assumptions that we make about the inputs that must hold in order for the outputs to be correct? For example, if you have a function, let's say a searching function, and that searching function assumes that the array is sorted, the fact that the array must be sorted should appear in the documentation. Structures and type definitions should also be commented. You should say what they're attempting to accomplish. Give some descriptions of the variables that compose the structure, that sort of thing. Control structures, things like loops and big blocks of if statements. One way of designing an algorithm is to do the comments first, and then to write the code in between the comments. So, it's more of a top-down way of programming, but you can look at the programming problem, say, okay, I'm going to have to do this, then I'm going to have to do that, then I'm going to have to do that, then I'm going to have to do that. You take all of these tasks, these programming tasks that you're subdividing the algorithm into, you put them in as comments, you write the code underneath which performs that subtask. And if you want to divide the subtasks even further, more power to you. The things that you want to explain inside of your comments are how and why. The why often gets left out. Right? So, how would be things like, using this library, if you're using a particular, known algorithm with properties, like for example, if you want to perform a search task and you've decided to use shell sort. Did I say search and then just say sort? Pardon me. If you want to perform a sorting task and you decide to use shell sort, say that you're doing an implementation of shell sort. If you're doing binary search, say you're doing binary search. If your algorithm contains elements of binary search, say this is a binary search-like approach. Label the types of algorithms that you're using. and explain why you're using them that way. You know, using shell sort here, not because it's faster, but because this is supposed to be going on a microcontroller. For those of you who are not as aware or not as familiar with the different sorting operations, shell sort's an interesting one. It's not the most efficient, but it's a sufficiently efficient algorithm. But its memory usage and like code footprint is very, very small. So it's still the best search, or it's the best sorting algorithm for embedded systems applications. But anyway, so these are all things that are correct to do inside of your documentation. This is what you shouldn't do. Do not explain what each line of code does. Not only does this constitute way too much writing, right? It clutters things up. There's this, like writing good documentation is kind of like writing good, prose. Just writing well in general. You do not want to waste the reader's time, and you do not want to present a lot of redundant and useless information. Essentially, if you think of it in a signal processing context, if you imagine all of the comments in your program to be a signal, right? You have like a signal to noise ratio, right? Which is kind of like, with radio signals, it's like how much noise is there in comparison to the actual information present. And if there's too much noise, then it becomes difficult to pick out the signal, right? So you want to have a high signal to noise ratio, basically. So it is not your responsibility to explain how the language works unless the purpose of your program is to explain how the language works, right? If you're just using the language, you can assume that whoever is programming in this language knows enough to be able to read your code without having the language explained to them. Not only does it waste space, it's a little bit patronizing. Do not leave sarcastic comments. Perhaps there's enough said about that, but there's a funny YouTube video you guys can look up if you want that is Valve developers leaving sarcastic comments in like the Half-Life 2 code. It's really funny, or maybe the original Half-Life code. At any rate, this is a good way to piss off your colleagues and get fired. Do not be emotional in any way. This is not your creative writing project. This is not creative writing in general. This is technical writing. It should be removed, like anything that has to do with you personally is not appropriate material for a comment, right? It's not like, like the person reading your commentary does not care about the emotional strain that you were under while you were writing this code, right? They don't care that it took you, 10 years and, 17 different people working with you, all of whom were not good enough for you to be able to produce this piece of code. We don't care. We just want to know how it works and why. There we go. Again, do not comment each line. By commenting each line, I guarantee you not all of those comments will be useful. And all you're doing is polluting the comment space with useless comments. Don't write anything you wouldn't want anyone else to see, including your boss. So don't slag your boss off in the comments. Again, a great way to get fired. Any questions about any of that? Yes?
Would we comment why we included a certain library?
depends on the library. In C, there's like, there's no need to explain why you include like standard IO, for example, or even standard lib or string.h or standard bool. If you're using one of the more out-of-the-way libraries, like signal.h, then I would say absolutely, I need this for X, Y, Z. Perfectly good thing to comment. Does that make sense? Yeah. Right? Because like anybody who knows any C programming wouldn't think twice about you including, stdio.h. Right?
So on top of that, are there any, I guess, common knowledge algorithms that wouldn't need to be, wouldn't need comments included?
Like within the body of a function? I wouldn't say so. Like even if it's something basic, like, performing a simple linear search, saying that is useful. Let's say include statements are much easier to read than the body of code itself, right? Make sense? Cool. You're looking at that video, aren't you?
Yeah,
Yeah.
funny.
Yeah, what's your favorite one so far?
The stuff that I can't say because this is a classroom.
Right. It's a funny video anyway. So,
I feel like they went down the list of don'ts.
yeah,
Yeah.
right?
It's every line.
Yeah. I mean, it's an excellent example of what not to do. So, in addition to comments in code itself, there are many different sort of documents that may surround a piece of software, both before, during, and after that piece of software is produced. So, in the beginning of a project, the very first thing, you start with specifications, right? So you'll produce things like high-level requirements and design documents. From these, you will refine into detailed requirements and design documents. So let's say, for example, anybody got an example of a software project for an example for this? Any ideas? Class conclusion? Anybody?
The Half-Life 1 code that they left all those comments on?
Half-Life 1. Okay, cool. So, high-level requirement for Half-Life 1. What do you think they would have thought about? I guess a lot of you probably don't know. How many of you know what Half-Life 1 is?
You know what it is or played it?
Know what it is?
I actually played it.
You've played it?
Yeah.
Yeah, me too. It's so very, very brief history. There was a software company that used to make, there is a software company that used to make video games called Valve. Anybody heard of Steam? A couple of you. Okay, so Steam is an online distribution platform for video games. For a while, it was sort of the best place to put a video game up if you were an independent developer. I think that's now the Switch. You make a lot more money on the Switch now. But anyway, Valve used to make video games, and Half-Life 1 sort of exists at one of these interesting thresholds in the industry, where before, everything was basically a Doom clone. So I don't know if any of you know the video game Doom, but
That's all I know.
yeah, right? Okay, so how many people know Doom?
I'm sorry, but
That's
who
kind of
knows
like
no
our-
Doom?
It looks exactly
I mean, I don't know.
like
It's
Doom.
kind of like
Yeah.
a fake 3D FPS game, right?
Yes.
But Half-Life just looks like Doom, but
You
a
mean
little
Doom
better.
Eternal? You know that
Yeah.
game was from the 90s?
Yeah. So here's how Doom worked, right? It wasn't like what we would think of as a true three-dimensional environment. All it was mathematical. Basically, they took a bunch of rectangles and stretched them according to, to try to simulate the geometry of a three-dimensional environment. Half-Life was a step up in terms of the game engine. So maybe we'll talk about the game engine behind Half-Life more specifically. So the idea with Half-Life is that we would produce a more realistic 3D shooter game engine with some physics, right? So like, you know, so some of our high-level requirements for this might be, you know, production of a three-dimensional game engine that uses polygon graphics, right? We might also include in high-level requirements, you know, something else about the game, something about the story that they want to tell, maybe, since it's a video game, right? From that, you drill that down and get to a more detailed view of what it is that you actually want to produce. So, you know, many companies at this point in time are developing three-dimensional graphics engines, right? Like Nintendo's got the one that they run Mario in. Sony's got, you know, a few third-party people who also have their own three-dimensional game engines. So the thing that, like, perhaps we pick some existing game engine and we want to say something like, I want to be able to render on screen 30% more polygons than that, right? So that brings it down to the level of a hard, testable requirement. So that's the main difference between high-level requirements and detailed requirements, is high-level requirements generally spoken by human beings. They're the design goals of the project, but they're not directly testable as artifacts of programming code because, you know, they're too vague. They're encoded in human language. What you do is you take those and you produce mathematical requirements in such a manner that you can actually test them so that you can actually know if you have achieved the design goals of the project. Obviously, this will have nothing to do with, you know, story or whatever. So, fine. From these detailed requirements, you can then produce testing plans and test documentation. Essentially, you can produce a set of black box or white box tests that will tell you if your program is meeting the detailed specifications, right? Then you have the system documentation. This includes the code comments, right? So according to this design, according to this, design methodology, you actually write your tests before you even write your program, right? Which is actually not a huge, that's not so very different from how things work in this class, actually. System documentation is the documentation of the code itself. Class diagrams, state diagrams, sequence diagrams, explaining how the code itself works. Then you get installation guides, the README files, and user manuals, which might also be in the README. Then, finally, you may have a final report it depends on the situation. If the software that you're writing is being handed over to another company wholesale, you're just giving it the whole thing, they will probably require a final report. And this is a joke about communism. So, Doxygen. We've sort of, flipped around quite a bit. Wouldn't it be just the most convenient thing in the world to be able to generate documentation directly from your source code? Doxygen is a popular tool for document generation. You can download it at this link, which I highly recommend. By the way, when I say have your laptop or computing device prepared for the exam, I mean also make sure you have downloaded, installed, and functional all of the pieces of software, all of the tools that we've been talking about in this class. So languages which are supported by Doxygen. C, C++, Objective-C, C#, PHP, Java, Python, IDL, Fortran, VHDL, and D. It can generate documentation for LaTeX, HTML, man pages, and other things as well. We're going to, in lab, focus more on the HTML side. It is possible to set Doxygen up in such a manner that you have a repository on GitHub. You set up a GitHub action so that Doxygen automatically generates HTML documentation for your project when you push changes to the repo, and those changes are publicly displayed as a web page with zero manual interference on your part. You can just push the code and the documentation is automatically updated. This is the awesome power of automation. So, to use Doxygen, you must first invoke Doxygen-G, which generates, that sets up a folder as being a Doxygen tracked folder. This generates a doxy file, which has many of the characteristics of a make file. They're kind of similar. It's kind of a similar idea. Basically, the doxy file hangs out in the folder that you want to generate the Doxygen documentation from, and Doxygen will automatically look for it whenever you try to generate documentation. The doxy file has a large number of configurable options, even more than Dwarf Fortress, which, if any of you have not heard of, don't look it up until after this class is finished. It's another one of those nerd trap games. So, it's important that the project name field be set, and if your source code is strewn among several directories, that will also need to be configured. Doxygen checks your working directory for source code files by default, and to generate the documentation, you just say Doxygen doxy file. So let's take a look. Well, anyway. COD, alright, fine. Doxygen-G for generate. Uh-oh. Come on. No. Why? There we go. There we go. Incidentally, this is apt, which is the package manager for Linux Mint. I don't know how I managed to get this far without Doxygen being installed. But. So, file, doxy file created. So, get it, doxy file. So this is what the doxy file looks like. There are a large number of options here. output language, output text direction, lots and lots and lots and lots and lots and lots and lots of things. Again, even more options than Dwarf Fortress. Good. So, so we'll just quickly spin up a C file. Good. So, now that we have our C file, let's talk about how to actually put in a doxy comment. So, to begin a doxy comment in C, you have to annotate your source code. Basically, you include a regular multi-line comment, the only difference being two asterisk characters at the start of it. That indicates it as a Doxygen comment. From there, Doxygen will parse out the correct positions. It will essentially look at the structure of the file and determine what that comment is supposed to apply to based on the position of the comment in the file. So it will also extract some information from things like function declarations themselves. So put these at the tops of functions, structs, typedefs, and files to have Doxygen document said construct with your comment. Doxygen also looks for commands to produce more informative documentation. So, for example, if you wanted to describe one of the parameters that a function is receiving, you use the @param to document that parameter. There are a lot of these tags that you'll be exploring in Lab 9. I'm going to leave it without too much further description. I'll just run you through the process of generating a quick one, and then you guys can explore this in more detail in the lab. So, let's say this small file is very small, made by me on day to day, etc., etc., etc. The time has come, the walrus said, to speak of many things, of shoes and ships and sealing wax, of cabbages and kings. There we go. Regular comment. Good. So, Doxygen, doxy file. There we go. So you can see that it's produced, by default, both LaTeX and HTML documentation. If we take a look inside, you'll see we have index.html, my project documentation. There you go. I must not have configured it correctly somehow. twice. Let's see here. Well, at any rate, that's the general process. There's more configuration that needs to happen. I need to move on to the pipes and filters stuff, so we're going to leave it there for now. Any questions? Yes.
What would we expect to see then?
What would you expect? Which who?
To see once you generate the document, just like a line of the documentation you wrote. Or-
So it'll produce a page for each source code file. It'll produce a page for each function within the source code file. Any of the documentation pertaining to, for example, a function, like if you describe any of the parameters, it'll put the parameters in a table and put the descriptions with each of the parameters. It'll give the overall description of the function. Yeah, that sort of thing.
Will it show the regular comment that you copied it or not?
No, that's the point. Yeah, because it's not tagged as a doxygen comment, right? Yes.
Can you give me an example about like how to use add param? Like add param. Can you give me an example how to use this? Add.
Oh, well, this doesn't really have any parameters, but you know, if we had, for example, you know, int myvar, you would say param myvar, my variable does something cool, something like that.
Oh.
Good. All right. Let's move on then. So, we've already talked about how to connect programs to other programs in various ways. So this will be a bit of a review, but let's go through it anyway. In Unix, there is an emphasis on writing programs to handle text streams because this is a universal interface. The whole idea of Unix is that all programs share the same type of interface. That is, standard input, standard output, standard error. If you're writing your program to work with standard input, standard output, and standard error, you are working inside of the universality of interface that is the thing that you want to do with Unix. So, we think about standard in, standard out, and standard error as being streams of data. So, how does one redirect a stream? Using a pipe, of course. So, this is the pipe character. When we, and this is stuff you do in Bash, right? So, if we have two commands and we put a vertical bar character between them, the standard output produced by X is taken up as standard input by Y. Make sense? Quick example. So ls piped to less takes the contents of that which was put out by ls and just pipes it into the less program, which is like a file viewer that's got a few more. It can do longer things. So ls-la, you can, use the less program to scroll through all of the things produced by ls. Using the greater than symbol, X's standard output is written to file Y. Reverse that, file Y is redirected to X's standard input. So, X outputs to Y, Y is input into X, right? If you put a 2 there, X's standard error is written to file Y, so that's selecting the other stream. And if you use the ampersand, then both standard output and standard error are written into file Y. Any questions? Yes?
Can you get standard error into Y? Like, the way that the pipe works, instead of a file?
Say that again?
Can you get standard error into another function instead of a file?
Oh, probably if you do two pipe, that probably would work. If that's, let's do something we know will fail, like copy nothing. Yeah, that did maybe work. Yeah. So if you don't copy anything, copy outputs to standard error that you're not copying anything, I've redirected that into less by putting the 2 in there. I think the only way to tell would be to do this. Maybe it didn't work. All right, maybe. There's probably some way to do it, but I'll leave that as an exercise for the reader. So, we've used redirection to and from files a number of times already in lab, so let's take a look at pipe character. This redirects a long output so that it can be scrolled through. So, like for example, make all piped to less. This also means that it does not appear in standard output. Retrieve the third line of a file. So, cat file takes a file and puts it to standard output, that's all it does. Head -3 takes the first 3 lines of the file. Tail -1 takes only the last line of the file, so you have as a result the third line of the file retrieved. This is a sorted list of all unique file extensions in the current directory. So ls, output to reverse, output to cut, reversed, sorted, and then unique. So let me get a so ls piped to reverse, ls pipe reverse piped to cut, d at the period. Option F1. There you go. Reverse that again. Sort. Unique. This is the idea with Unix. Many small programs chained together to achieve great purposes. Make sense? Any questions? Yes.
What does F1 do?
I don't know. something to do with cut. So fields. Select only these fields. Also print any line that contains no delimiter character unless the S option is specified. Yeah. So, for example, if we pull this back to here and select the second, then we are selecting the second half of that cut, right? So actually, a more efficient way to do this whole thing would be to remove the reverse, ls cut, F2, sort, unique, C. Same thing. The reverses are useless, as it turns out. You can just select the second one. Anyway, so, good. You can even combine piping with loops in order to loop over the output of different commands, kind of like a for loop in Python. So, ls piped to while read item do item exists in this directory, done. This will take the results of ls and pipe each result, assign those piped results into item, and then loop over each of the items, which is kind of cool. However, sometimes you're in a situation where you don't want to redirect something specifically to the standard input of the function. Perhaps the standard input isn't configured correctly. You would rather redirect it to the arguments instead. In this case, if we try to do this, it'll try it like ls piped to rm. It will attempt to delete the entire output of ls, which of course is a lot of file names, which is, not something that's going to work. I think I'll try this with something a little less, let's say, so this is a good one. So the difference is something like ls cat, right? Which just displays everything, and ls piped to xargs cat. So that's happened because there are a lot of images in this directory. Let's go to something maybe a little less let's try topic 3. That should have some cool stuff. No code directory. Topic 4. Come on, work with me here. Topic 6. There's a code directory. All right, ls, oh, but it's got executables. Okay, ls star.c, redirect to cat, just shows me all of the C source files, right? I suppose I could have done this in the other directory, but whatever. Xargs cat does something a little bit different. Rather than simply taking standard input and processing that as the thing that cat is operating on, if we use xargs, each file name that is inside of the standard input that's being sent to cat gets used as an argument to cat instead of being directed to its standard input. What that in effect does is it displays the contents of every C file in this directory instead of simply displaying the names of the files in the directory. Does that make sense? We are redirecting from standard input into an argument. So, yes. In this above case, the output of ls, which is separated by white space, is broken up and fed into RM individually. In our case, we're using cat instead of RM because it's non-destructive. This command will succeed and perform what we want to, whereas the other one will not. So, good. All right, so we can direct. So, let's say we've got ls, right? It produces a list of file names. Let's say file1, file2 .c, file3.c, right? So this would be standard output. For cat, we've got two ways of inputting into the function, right? Or inputting into the program. We've got standard input, and we've got arguments, right? Without using xargs, the pipe character pipes this to standard input, which in the absence of like a file, cat will simply operate on standard input, assuming that the entire contents of standard input is the file that you want to see, right? What xargs does is it redirects that to the arguments. So you get file1, file2, file3. You're constructing a bash command. Does that make sense? Maybe a little bit? Question?
So like in this example, the arguments are to copy the name that all has .text
Yes.
into this directory. So the arguments are the copy in the directory.
Yeah. So yeah, this is a somewhat. So this is using some options on xargs. We can select the place in this command where things get inserted.
Okay.
Right. So. So, find in the current directory all things with the name star.txt. So this is a bit like a blob pattern that's recursive on directories. So, for example, we're going to talk about the find command in a bit. Find dot dash name star.text or star.c. Oh, it's got to be in quotes. There we go. Right. So find is able to find every C source code file inside of the slides directory, right? So again, it's a bit like star.c, but applied to this and every subdirectory. So if we wanted to take all of these C files and copy them to a temporary folder, right? xargs cp-temp, right? let's imagine that the temporary folder exists. I'm not actually going to perform that top command because it, I believe, will do something destructive. Make dir temp. There we go. Essentially, if you try to do this way, you get are not specified omitting directory temp. So remember the usage of copy, right? So with copy, you get two arguments, and you copy from argument 1 to location specified by argument 2. So because the way that xargs works is it by default drops everything in at the end, this means that we have to figure out some way of inserting the xargs output into the middle of a bash command, because we want this here to be /temp, right? We have to try to insert it here. So the I flag allows us to select where and how many times the argument will be inserted into the target command. So -I, you then specify a character, right? In this case, I'm using the character X. That will be the position where the xargs output is placed. So if I say find these, pipe that to xargs -I x, copy from x to temp. There we go, it didn't complain. CD into temp, and uh-oh. Okay, what did I do wrong? All right. No, I'm still on temp. All right, so we got all those. Oh, yes, I know. Okay, so in this case, we've actually got one more problem. So xargs is splitting on white space, right? How much white space is contained in this? Quite a bit, right? White space, white space, white space. So it's actually splitting up and thinking each one of these is an argument. So nothing worked. There's another option to get around even this. And that's print 0 on this side. Or let me actually retrieve this guy. So you print 0 here. And on xarg's side, you add the -0 option. And hopefully, that worked. Damn it. All right. We've got, I'm going to skip ahead. Yeah. There we go. So, maybe we can just cap this to something less complicated at the moment. Right? So that is doing what it's supposed to be doing. Okay. CP. I think that's the default one. -temp. Great. I should try not to get too far ahead of myself. Ah! There, it worked for some reason. Cool. Well, there you go. It did work. Maybe I was just looking in the wrong folder or something. Anyway, there they are. Question?
Did you just use a backslash instead of forward slash?
I might have, yeah. Yeah, that might have been the problem. That would be funny. Let's see.
Like after X?
Backslash, yeah. Yep, that was exactly the problem. Nah, there we go. Whoops. My brain was in Windows land. There you go. Always use backslashes. But yeah. So there we go. The example actually worked. So let's talk blob patterns. So we've been using blob patterns this whole time. Anytime you put an asterisk in a file name to select multiple files of a particular pattern, you're actually using blob patterns. Blob patterns give us a way to represent file paths that match a particular pattern. We use special characters to represent multiple characters in multiple ways. So, for example, question mark, single character wildcard. Character is required to exist. So, for example, if you wanted to select all files in a particular folder which have only one that have only one letter in their file extension, let's just say, you would say, there you go. And of course, they're pretty much all C files, except for a couple of O files and a couple of H files, right? If you want all files with two characters in that file extension, you use two question marks, etc. You guys get the idea? It's a lot like the asterisk, except it is required to exist, whereas the asterisk will match things that don't actually exist. Oh, it's misaligned. The asterisk is 0 or more continuous single character wildcard characters. Effectively, it replaces any number of characters, including no characters at all. However, anything that's not this asterisk still has to match. So, star.c obviously selects all C files. We can also choose between multiple specific strings which are comma separated. So, for example, if you wanted to sort of target all C, O, and H files, we can delete all C, O, and H files in that manner. So if you want, you can do something like find all PNG, GPG, and JPEG files, which didn't work for some reason, probably because I've got these here. Oh, jeez. Numblock is my worst enemy. Oh, well. Interesting. Well, at any rate. So, blob patterns can be used for more than just file matching. If you want to produce a series of alphabetic characters, you can use this brace and double dot notation using Blob. Basically, how Blob works is anything that is input to the bash prompt is scanned for blob patterns, and those blob patterns are expanded prior to any of the commands being executed. So a good way to check your blob patterns is using echo, right? So if we echo, for example, star dot A to E, there we go, right? You know, we can produce things that aren't even file names, right? We can produce all kinds of different strings using blob patterns, which may be useful in some contexts. One interesting thing to note is that this works along the same principle as patterning in C. Note that we are including like regular ASCII characters here, right? I'm not sure why this is in reverse. It's kind of interesting, but notice that we get the ASCII characters between the two alphabetic sets printed using this blob pattern. Furthermore, we can also do numbers in the numeric sense. So we can go from 10 to -10, and that counts us down from 10 to -10. Just a quick way of doing that. So, for example, if you wanted to, if you had a series of file names, file 1, file 2, file 3, file 4, you could do something like echo file 1 through 6 dot text, and you can generate all of these file names. Now, it's tricky to do that, that's a lot of typing otherwise, right? So that's kind of useful. Not to mention, if you're doing bash scripting, this could be a variable, right? So, you could generate a number of file names which pertain to some, the return result of some, other program. Make sense? Any questions? Okay. So, one other brief note, just because this is, another one of these kind of Linuxy things, in general, you want to try to avoid using blob pattern special characters inside of any, regular file names that you may be using. So, and this includes space characters. I've talked about the space character thing before. So, asterisks, not a thing you should include in file and folder names, nor curly braces, nor question marks. Just don't include them in file names in Unix environments. If you really, really, really have to, you can use a backslash to escape a character. But, again, highly unrecommended. Or not recommended. Unrecommended? If somebody recommended it, I unrecommend it. So, good. So let's talk about the find command. The find command allows us to locate files in our file system using blob patterns. So, unlike CP and RM, which automatically recurse through directories, so essentially, we use find. We specify a starting directory, which can be relative or absolute addressing, right? So that's why it's very important to include a period here if you want to search in this and all subfolders recursively. The period designates the current working directory. If you remember that, you then have a number of flag options. You specify either name, or it's also possible to specify path, and then you provide a blob pattern. Find will recursively find all files matching said blob pattern in whichever folder is specified and all subfolders. So, with CP and RM, in order to perform operations recursively on all subfolders, you have to specify the R option, -R. Find just does it automatically. To find how deep find goes, to find matching files, use the max depth flag. So if you want to specify, okay, I want you to find all files of a particular file extension within 5 directory depth of home, this is how you do this, because this is home, all right? Tilde is an abbreviation for the home directory. You set max depth equal to 5, and name is star.c. Make sense? The F flag tells you to target files only. The D flag tells us to target only directories. You can even use flags to invoke Boolean operations and perform multiple tasks at once. So, and this is one of those places where it's highly possible to use other means and mechanisms to achieve the same results, right? To say find all C and H files in all, find all C and H files, you could specify a blob pattern that catches both of those. Or, another way to do it is to use the OR flag here, so we get name C or name H. And this is like one of those crazy instances where like the position of flags relative to other flags actually impacts, the manner in which the task is performed. You could find all files which are not Python files, right? And you can find all directories starting in the current context matching both of these blob patterns, right? I feel like you guys are kind of getting lost a little bit. No? Maybe just like this is like the technical stuff that's like a little bit more, yeah?
Just for the last, like the directory, does that mean it's looking for directories like lab1.txt?
Yes. Yeah.
Or so the 2 stars though, does that mean it's for 2, like it would be lab 0, 1?
Well, if that was what we wanted to do, then we would be, yeah, actually, why are there?
Or would you use the question marks?
Yeah, why wouldn't you use the question marks? I think you would have to use, let's see here. So, find the name. Let's just see what this does. Yeah, 2 stars does work, but grabs everything that's got a, okay.
What happens if you just have 1 star?
same thing. Which makes sense, right? Because like, you know, two stars next to each other are redundant. Two question marks is gives you just those. So notice, although these are directories, you know, they've still been matched here. And it seems that this information is out of date now because the D option is being deprecated. And yeah, question.
If you put -D, why did it find the files that aren't directories?
I think because it's not doing what my source material said it was. That makes sense. I'll make a note to update these slides, which is kind of annoying. All right. So, all right. I think we need to keep moving because yeah. So we might have to finish this topic next on Wednesday, which is fine because we covered the Doxygen stuff first, and that's the lab tomorrow. And the lab on Wednesday will be this stuff, so it all works out. Anyway, so this is a somewhat famous XKCD cartoon about how regular expressions are useful. So we're going to learn about regular expressions now, which are kind of a similar kind of idea. So regular expressions are kind of, they're an interesting beast. When you're writing a regular expression, it's a little bit like they're kind of like blob patterns, but not really. There's a model of computation, which is, if you haven't heard about it yet, you probably will hear about it by the end of second year, called Finite State Automata. Have any of you heard about automata, finite state automata? So it's very, very rough sketch. Let's see here. It's something like this. So if you have, let's do capital letters. A, B, C. D, something like that, right? So this is what you would call either, like from one perspective, a state machine, from another, finite state automata. So this is a way of matching sequences of symbols. So this machine describes a series of symbols, like a set of symbol sequences, right? So assuming we start here, right? Or sometimes they just draw a second thing around it. So some of the patterns that match this guy, A, B, C, D, and let's say that's N, A, B, 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 C, D, right? A, B, C, D, C, D, C, D, right? These all trace paths through this machine, right? A, B, 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 C, D, C, D, N. Make sense? Regular expressions are a way of encoding these machines as strings, and the way that they're generally used is you have a big chunk of text, like say a big file or something. You're trying to look for particular things which match the patterns given by the regular expression. Regular expressions are extremely useful. They're also shall we say, a pretty obvious tell that somebody's been cheating and using Chegg for their assignments when they give me a solution in Comp Sci 1MD3 that requires regular expressions and knowledge thereof. Because, you know, you don't know this in first year. So, regular expressions. Blob patterns are wonderful for managing the file system, but lack the expressive power to be used on larger targets such as the files themselves. Enter the regular expression. Based on a model of computation called Finite State Automata, which is beyond the scope of this course, but you'll learn about them in discrete math courses, I believe, if you take them. Similar to blob patterns, regular expressions allow us to write special characters, which may be then used to test or search large groups of characters, for example, files. An excellent online tool for testing and debugging large and small regular expressions is https regex101.com. It's a very useful one. Regex101.com. There we go. So, for example, you copy in some text, and you say something like blob. And it'll highlight all of the matches, right? Or, for example, TE. All of the instances in this piece of text where TE, the characters, occur. So, we're going to talk about a bunch of these guys. So, essentially, in order to use regular expressions, there are some operations that you have to know how to perform on them. Notice that I used the term debugging in reference to regular expressions. Regular expressions are programs. It's like a sub-programming language again, right? They're like, oh my God, how many programming languages are there? Frig, man. But yeah, it's like a programming language. All it does is match text. So, vertical bar separates alternatives. So, A bar B gives you either A or B. So, in this example, TE or OM or A space matches every instance of those two characters occurring inside of this piece of text. Does that make sense? Notice that there's kind of implicit braces around this phrase, right? It's not T, E or O, M or A space, right? If you want to do that, you can actually. It's not going to match anything in this, though, unless I change what the letters are. So, right? So that's another lesson about regular expressions. If you want to group things, you put them inside of braces, right? So, P, well, actually, I could probably find another example, but anyway. Obviously, the O and the A go unused here. I'm sort of exclusively matching P, A, T. or P-A-T-T, but you know, it is what it is. Make sense? Make sense so far? Yes, that's actually my next thing. Round braces determine how a regex operator is bound. So, for example, we have Tom A. Auto produces tomato, tomato. So, if we have a regular expression like E, S-A, X-A, N-M, that matches N-M, X, E-A, S-A, and the X here. This is the lorem ipsum text, which is has a lot of, it like goes all the way back to like 1600s, pretty compressed. Yes?
Why did it match PAT twice and PATT once?
I don't think it did. We've got 3 matches here. That's the other nice thing about this tool is it'll like display to you what the matches are, right?
Oh, it's just highlighted.
Yeah, it's just a highlighting thing. But yeah, like, you see how, you know, this is actually much more useful than I originally gave you the impression of, because it tells you the match information as well. When doing regexes, it's useful to do this in the same way that it's useful to use Python tutors to write programs in, so you can see what's actually going on. Cool. So, a postfix plus specifies more than one or more occurrence of a character, and a postfix asterisk specifies 0 or more occurrences. So, essentially, if this were a regex, right, it would be A, B plus, C, D plus. Because in both cases, you have to have at least 1 in order to reach the end point. Make sense? And there's also the single character wildcard period. So if you don't care, for example, you say m.n or something more useful, f.r, no, n.a, n.dot, fine. That is all occurrences of the letter n followed by 2 characters, which of course, you know, it doesn't matter what 2 characters they are, but only 2 characters. Whereas, n dot star matches everything up to the end of a new line character. So anytime an n occurs in a line, it targets the entire rest of that line. Because we're having 0 or more repetitions of a wildcard. Question?
Why doesn't it target all ends? Well, I guess. So, I guess.
Oh, like this one as well? It probably does, it's just being obscured.
I mean, so under the 3rd highlight, the row under has an N in, I guess, the sentence.
This one?
No, the highlight under that.
This guy?
Under
It's
that.
not highlighted.
Well, this one has an N here and an N here, right? So let's, yeah. Yeah, it's not doing them recursively. It's going for like the largest matches possible.
I guess what I'm asking is, it's for the fourth line from the bottom.
Fourth line from the bottom, this one?
Yeah, there's an end there. Oh, yeah, it didn't highlight that line, so I was just wondering why.
Oh. Well, it did, it's just a little faint.
Oh.
Yeah, it's hard to see, but that is actually match 7. Yeah, so it's not targeting any, like it's going for only the largest matches. But yeah, makes sense? Any questions about that? So I wanted to talk to you guys about something that was kind of interesting that happened at the conference that I was at. We'll save rep for tomorrow, or for Wednesday. I wanted to talk to you guys about something that I saw which was fairly interesting at the conference that I was at in Romania very recently. There was a paper about regex attacks. It turns out it's actually possible to maliciously construct a regular expression so that it requires a large amount of computational time in order to perform the search. I think it was something like, I forget now, but I think it was something like options plus wildcards in combination can explode the computation time that it requires in order to perform the regular expression. So basically, if you've got if you've got a web service and it's using regular expressions, and there's some way that a person might write something that gets, either write a regular expression directly or write something that gets turned into a regular expression that then is executed by your system, they can construct it in such a way that it effectively functions like a DDoS attack, where it just exponentially explodes and consumes all system resources until it's done this extremely long calculation, which will take your server down. And the paper that I was seeing was like a tool for predicting whether or not a regular expression will cause that type of explosion prior to actually running it, which is very useful. I forget what the name of the tool was, but yeah. So regular expressions are a very hot topic. Even to this day, there is still active research being done about them. So yeah. Any questions about this or anything else? Okay. So Wednesday, we're going to take these guys and we're going to learn how to do them over our file system using grep. So that's what we're going to cover, and then we're going to talk about more C stuff. Glory be. So, thank you very much for your time and attention, folks. Good luck on the lab today.